Welcome to this session. This session introduces the first appetizer on how to evaluate Jacobian of functions. So the first problem, you are given x equals to r cos theta, y equals to r sin theta. Then you are asked to evaluate Jacobian of xy with respect to r theta, Jacobian of r theta with respect to xy, and then the product of the two Jacobians. So this is simply the transformation between the rectangular coordinates and the Cartesian, rectangular coordinates and the polar coordinates. If you might remember from your basic geometry concepts. So solution. So the first part, Jacobian of x, y, with respect to r theta is the same as the determinant partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. This by definition. And from the functions we have, if x is r cos theta, then partial x partial r should be cos theta. If x is r cos theta, then partial x partial theta is derivative of cos is negative. So r sin theta. And partial y partial r is sin theta. Partial y partial theta, sine is cos, so this will be r cosine of theta. Now this are just a 2 by 2 determinant, so it should be easy to calculate. Cos times r cos theta will be r cos squared theta. Minus will be plus. Sin theta times r sin theta is r sin squared theta. And this expression, r is common, then cos squared theta plus sin squared theta. And we know that sin squared plus cos squared is 1. So therefore, partial x, y, partial r theta, which defines Jacobian of xy with respect to r theta, is just r, since this is 1. And then, so Roman 2, we'll have to calculate partial r theta, partial x, y, which is Jacobian of r theta with respect to xy. Now, we have been given that x is r cos theta and y is given by r sin theta. Squaring these two equations, we have x squared equals to r squared cos squared theta, y squared equals to r squared sin squared theta. And when we add, we get x squared plus y squared equals to r squared into cos squared theta plus sin squared theta, whose value is just 1. So that means in this transformation, x squared plus y squared is just r squared. And then if you divide y over x, we get r sin theta over r cos theta. So r and r, sine over cos is tan. So tan theta is the same as y over x. So we are going now to use these two, this and this one, to get this Jacobian of r theta with respect to xy. So by definition, this will be the determinant partial r partial x, partial theta, partial, not partial theta, so partial r, partial r, partial y, then partial theta, partial x, partial theta, partial y. Now, if let's do some differentiation here. So as I said in the first session, if you are weak in differentiation, partial differentiation and determinants, this topic will not be easy to you. So please get some time and watch videos on partial differentiation and determinants. So if x squared plus y squared equals to r squared, so let's see how we get partial r partial x. So we are supply partial x to every term, partial x, partial x to r squared. So here the assumption is that r is a differentiable function of x. So this will give us 2x. And then this is 0 because there's no x here. This will be 2r, but partial r, partial x. But this implicit differentiation. So divide through by 2r. So partial r, partial x is x over r. So here we write x over r. And then partial r, partial y, we do the same thing. So supply partial y to each of the terms here and assume r is a differentiable function of y. So partial y of x squared plus partial y of y squared equals to partial y of r squared. So this would be 0 because there's no y. So this would be 2y, and this would be 2r, but partial r, partial y, because r is assumed to be a differentiable function of y. So dividing through by 2r, we will get y over r. And then the relationship for x, y, and theta was that tan of theta is the same as y over x. So tan theta is the same as y over x. So if you were to draw a right angle triangle, if you put your theta, and then from Washachota, tan is opposite of adjacent, cosine is adjacent of hypotenuse, sine is opposite over hypotenuse. So opposite is this, adjacent is this. So this will be x squared plus y squared square root. Now, to find partial theta, partial x, you supply partial x on both sides. And the assumption is that theta is a function of x and y, or a differentiable function of x and y. So partial x of tan theta equals to partial x. Remember, this can be written as y over x can be written as y x raised to power minus 1. So this is the same as y x raised to power minus 1. And when you differentiate a tan function, you get sec squared function. Please check your differentiation. And because theta is a differentiable function of x, so you attach the theta dx, and then is equals to, now with respect to x here, just drop the power, so we'll have negative, and then subtract 1 from the power, so it will be -2. So we'll have y x minus 2, or just say minus y over x squared. But sec theta is the same as 1 over cos theta. So from this triangle, cosine is given by adjacent, so x over hypotenuse. So the reciprocal will be hypotenuse over adjacent. And when we square, this is what will define the sec squared theta. So sec squared theta will be given by x squared plus y squared, and then over x squared. So it's like we have give me just this space here to solve this. So we have x squared plus y squared over x squared partial theta partial x at this point here equals to -y over x squared. And remember, x squared plus y squared is r squared. So I multiply by x squared over x squared plus y squared. I multiply by x squared over x squared plus y squared. So this and this cancels out. So this will be -y over x squared plus y squared. But x squared plus y squared is r squared. So -y over r squared. So this will give me -y over r squared. And similarly, let's discuss partial theta partial y. So still this same triangle will help us to understand what you're supposed to do. So the relationship is that tan theta is given by y over x. So you supply now partial y on both sides. So this will give you partial y partial y of tan theta will be sec squared theta, but you attach the theta dy because theta is a function of both x and y. So it's a differentiable function of x and y. So equals, this will give us just x raised to power -1, or simply 1 over x. So sec squared theta, as we have done, is the same as x squared plus y squared over x squared, which is the same thing as r squared over x squared. So r squared over x squared partial theta partial y will be given by 1 over x. Now we multiply by the reciprocal x squared over r squared, x squared over r squared. So this and this cancels out, this and this cancels out. So partial theta partial y will be, now 1x cancels here, so I have x over r squared. So this part you put x over r squared. So therefore, this is a 2 by 2 determinant, which should be easy to calculate. So we'll have x squared over r power 3 minus will be plus, y times y is y squared, r times r squared is r power 3, which is the same as you put under 1 LCM. So this will be x squared plus y squared. But from definition, x squared plus y squared is r squared. So over r power 3, this gives us 1 over R. So therefore, partial R theta partial xy is 1 over R. Now Roman 3 partial xy partial R theta times partial R theta partial xy. This we got the answer as R, and this one we have gotten as 1 over R. So this gives us 1. So that's how we solve that problem. The next session, we'll see how this result will always give 1 in general case, regardless of the way you define x and y, provided that there are two functions which can be expressed in terms of the other, and then we can get the Jacobian and the inverse of the Jacobian. The product will be given by 1. We'll see that one, the proofs of properties of Jacobians. Thank you. And then maybe if you have problems on differentiation, what we've been doing here, please check calculus videos on implicit differentiation. It will make you understand easily what is happening for us to get these values in this second determinant. Thank you.